Today we are going to start talking about the electromagnetic induction, or more precisely, we are going to talk about Faraday's law. Now, this is a very important law actually, because it is the backbone of modern civilization, for the simple reason that all the electric power generated today, probably apart from the photovoltaic maybe, is actually based on electromagnetic induction and on Faraday's law. So this very simple relation, which we will introduce shortly, is actually at the center of today's civilization, because it is the base for generation of electric power. Now, historically, we know, first of all, let's talk historically about when this was discovered. I mean, Faraday's law, when it was discovered. First of all, we know that if you have a magnetic field and you change the source, you vary the source that generates that magnetic field with time, then the magnetic field can vary in time. Okay. Now, in the 19th century, in particular in 1831, Faraday and Henry, doing experiments, showed that an electromotive force can be induced in a circuit by changing the magnetic field that penetrates the plane of that circuit, So it was the first time where an electromotive force was induced not by a battery, but by a varying magnetic field. Now, and the results of this experiment, as were quantified by Faraday, are known as Faraday's law of induction. And this phenomenon is called, that is, generation of electromotive forces by varying magnetic fields, or between parentheses magnetic fluxes, is actually known as Faraday's law of, is known as electromagnetic induction. Now, so in this phenomena, we have electromotive force or a current is generated by a varying magnetic field, and this means that we have an electromotive force generated that induces this current. And the meaning of this is that you don't need a battery in a circuit to generate the electromotive force, and so the current actually. You just need a varying magnetic field in this circuit. This is the idea of induction, okay, electromagnetic induction. Now, Faraday's law is a quantitative statement describing the electromotive force that is generated by this. We will talk a bit about what we call the microscopic version of Faraday's law, if you like, as it's related to Maxwell's equation, towards the end of the chapter. For the time being, let's just describe some activities that will tell us how does this current appear in the most simple setup. So for this purpose, you consider a meter or a galvanometer, that's a microammeter, which is a device that measures current, okay? And you connect this loop to the ammeter in series, so this is now a closed circuit. Now, under normal conditions, without doing anything, there will be no current passing here, because if you don't have anything, I mean, assume that you don't have the magnet, you don't have anything, you just connect this ammeter to this wire, and then look at the ammeter. It will read nothing, because there is no battery, there is no current flowing in the circuit. Now, however, if you bring a magnet, okay, and move this magnet towards the loop here, okay, towards the circuit, then you will note that the ammeter will start reading a current. Okay? Now, if you move the magnet away from the circuit, then the current also, while you are moving the magnet, will read a current, but it will be in the opposite direction. So note here we have -1, here +1, whatever are the units, microampere, nanoampere, whatever is that. So you have minus and plus. Minus plus here means they are in opposite direction. So while you were moving this, okay, it read -1. While you are moving it away, it read +1. That's the current in the opposite direction. Now when you move it in or out and stop your hand, that is, you move it in and you stop. Once you stop, the current goes down to 0. Although the magnet is still there. The magnet is still there, but now you are not moving it neither in or nor away from the loop, and so the current will be 0. So the current will be induced only while your hand is moving towards or away from the loop in this case. Okay? Which means that when the magnetic field or the magnetic field lines that are crossing this loop are varying in time. Now the same, of course, could have been achieved by keeping your hand fixed but moving the loop towards your hand. So it's effectively the same thing, okay? So you can move the loop towards your hand, or you can move for example, you can move the loop away from your hand. In this case, the result will be the same. But once you stop the motion, and even though that you have a magnetic flux still, magnetic field lines, they are still penetrating the loop, but they are not changing with time, then in this case there is no current. Only when there is a variation in the magnetic field lines that are crossing the loop, you will have a current, an induced current. So keep this in mind. This is important. So this is a very simple activity that demonstrates how this is the induced current, and so the induced electromotive force. Okay? So when you have a current, having a current means you have electromotive force, because electromotive force is actually the cause of the current. You have induced electromotive force, then you have a current induced. Actually, if you want to get deeper, it means that you are inducing an electric field, because as we have learned when we first learned about the microscopic description of current, that current actually emerges because there is an electric field driving drifting the charge carriers, okay? And so we have electromotive force and we have current. So actually here what we are talking about is that to have electromotive force means a bit deeper, if you look, that there is an electric field. So we have an electric field induced. Now we will come to this towards the end of the chapter. For the time being, let's say, okay, this changing number of, when we have a variation in the number of lines crossing the circuit with time, then we have an induced electromotive force, and so an induced current. So let's look at it this way. Now the experiment done by Faraday, it's just for historical reason. It's more or less, this is more or less the same experiment, except I'm sure that Faraday didn't have this digital ammeter here. So that experiment was roughly the same. So he had this circuit, which is called the primary circuit. This is called the primary loop. So this is a battery, there is a switch, and this loop or this coil is wound around an iron core here, and this is an insulated wire, so it is not in touch with the iron. The iron here is just to strengthen the magnetic field that is generated within the coil. We remember just in the last class, we have seen that if you have a coil, a solenoid, for example, then there is a magnetic field within inside that solenoid. Okay, so when you connect this and there is a current passing through this coil, then there is a magnetic field here. If you put an iron here, the magnetic field will be stronger. That's the only purpose of this iron actually. But it is not in touch with the coil. The wire of the coil is insulated. So this is a battery, and this is connected to battery. When you close the switch, current flows here, and the magnetic field is built up within this solenoid, and so within this iron. On the other hand, there is the secondary coil. The secondary coil is just a coil. It is not connected to any battery, but it's connected to an ammeter. So this is a closed circuit now, but there is no source of electromotive force here. So we don't have a battery here. So what we observe here is that, so this is what we are talking about. Now, when you close the switch, okay, you observe, you look at the reading of the current. At the instant the switch is closed, current flows. And this measures immediately a current. But this current, okay, after a very short time, it measures a current and then measures again 0. So what's happening in this case? Because when you close the switch, then the current is still building from 0 to the value, to its steady value in the circuit, okay? Now during this time, the magnetic field in the coil and so in the iron is changing, okay? So we have a varying magnetic field. During this very short period, you will see that this reads a given value and it comes back to 0. When it comes back to 0, when the current reaches its steady value, okay? And then after, so just you get a current and then you get, after that you get 0. So the current builds up only, appears when the current in the induced current, I mean, that this measures, the current appears only when the current here in the primary coil is still building up, or in other words, the magnetic field here is still building up, which means it is still varying with time. Now, when you, after the ammeter is switched and you reach the steady state and this reads 0, open the switch now. When you open the switch, you immediately notice that you will have a current for a very short time, and then that current will die and go to 0 again. So again, when you open the switch, the current in the circuit will go from the value that it had to 0 again. Now this does not happen instantly, it takes time. During this time, in which the current is changing from its steady value here to 0 as you open the switch, the magnetic field here is changing in time. From a given value, it's decreasing to 0. So during this time, the magnetic field is varying within this coil also, and therefore the current will be induced. However, it will be induced in the opposite direction. So in the first case, when you close the switch, if you get a positive here, you will get a negative here, and it will die quickly, and it will give 0. So this was the experiment by Faraday, and from which we conclude the following: an electric current can be induced in a loop by changing magnetic field. Okay, and this would be the current in this secondary circuit. The induced current exists only while the magnetic field through the loop is changing. Okay, so the induced current exists only when you have, not when you have a magnetic field, but when you have a changing magnetic field. So when there is a magnetic field but doesn't change, there is no induced current. Okay, so what induces the current is not the magnetic field, it is the change in the magnetic field. This is what we conclude from Faraday's law. Now, this is dually, this observation is expressed as an induced electromotive force is produced in the loop by the changing magnetic field, roughly speaking. And so the actual existence of the magnetic flux is not sufficient to produce the induced electromagnetic field. The flux must be changing. What flux we are talking about here? Well, you remember at the first experiment, when the first demo that I have discussed, I was talking about the magnetic field lines. I was saying, okay, we have magnetic field lines that are changing. Now let's remember that we have related this magnetic field lines to flux before that, when we talked about the Gauss law. You remember in that case, we defined something called the flux of the electric field, which was the proportional to the number of electric field lines that were crossing a surface normal to that surface. Okay? So here also, when you have a magnetic field, and this magnetic field is crossing some surface, then actually we can define in the same way a magnetic flux. And this is important because, as we will just see, the quantitative relation between the induced electromagnetic, induced electromotive force and the magnetic field is actually between the electromotive force and the magnetic flux. of the magnetic field. So let's move first to define the magnetic flux of the magnetic field, and which will be exactly follow the same lines as we did in the case of electric field. So consider here this surface, and this surface is placed in a magnetic field. I'm showing only one line of the magnetic field, but of course this doesn't mean that the magnetic field only exists here. No, there are magnetic field lines here, and this surface, which is an arbitrary surface, not necessarily closed surface, any general surface. Okay. Now this surface now is in this magnetic field. Now, so this is the magnetic field. The area element here, I take a small area element here, which I call it dA, and the magnetic field direction at the this area element is shown as B. Now, and this vector dA, as you know, it is a vector whose magnitude is equal to the magnitude of the area element, but it is, by definition, perpendicular to the area. Okay, this is exactly the same dA that we have encountered before when we talked about the electric flux. Now, the electric flux, the magnetic flux, the flux of the magnetic field through the whole surface is defined by this expression. Note the similarity between this and the electric flux of the electric field. The integral here, of course, we used to put an S here. I didn't put it here, but it has to be understood because it's integral over area. So this is the integral of B dot A over a surface. If you replace this B by E, it will be just electric flux. Okay, so it's exactly the same. What does this mean? Let's remind ourselves, what does it mean? It means find B dot dA, find the component of B normal to the surface, yani parallel to dA here, okay? Multiply it by the area and do this for all the dAs here and take the limit when dA goes to 0. This is this integral. Okay? So this is the definition of the flux of the magnetic field through any surface. This is the surface integral. Now, you recall also, just as in the case of electric flux, if the surface was like a plane or then the magnetic field was constant over the planar surface, so that we have only a single angle between the B and all the dAs, then in this case, this reduces to this simple expression. So you have a magnetic field that is uniform over the surface, and the surface is a plane, therefore the area, the angle between the area and the magnetic field is a single angle, which is cosine. You can define cosine theta. So this is a very special case of this when you have a uniform magnetic field. Uniform means constant in magnitude and direction over a planar surface. So you get it, and this is the expression for the flux in this case. For a general magnetic field and a general surface, this is the expression for the flux. Now, unlike the electric field, the magnetic flux has, which is in Tesla times meter square, of course, because it is magnetic field strength multiplied by area, Tesla meter square, has a special name, which is Weber. It is Weber, okay, and it's abbreviated as WB. So the magnetic flux is measured in Weber. Now let's consider here an example for the special case when we have a uniform magnetic field and we have a planar surface. So we have this planar surface here, as you can see, and so dA here is the same. For all dAs here, it is always pointing in the same direction because this is a plane. The magnetic field is uniform, and therefore the magnetic flux here is BA cosine theta. In this particular case, the angle between A and the magnetic field is 0, so cosine theta is 1. This is the maximum magnetic flux. Now, on the contrast, if you have the, this plane rotated so that dA is perpendicular to the magnetic field, or the magnetic field is parallel to the surface, then in this case, the angle between B and dA here is pi over 2, cosine pi over 2 is 0, so there is no magnetic flux because there are no magnetic field lines penetrating that surface normal to it. So the flux is 0. So this is the idea of the magnetic flux, and as you can see, exactly the same as what we had for the electric flux when we discussed Gauss' law, before we discussed Gauss' law. So having understood or defined what magnetic flux is, now we move to formulate Faraday's law. Faraday's law says the electromagnetic force induced in a circuit is directly proportional to the time rate of change of the magnetic flux through the circuit, which you put it mathematically in this, say. The left-hand side is the induced electromotive force, and the right-hand side is the rate of change of the magnetic flux with time. This minus sign, I will talk about it later. Let's leave it aside for the time being, and let's think of it as the absolute value. Okay? So the electromagnetic force induced is proportional to the rate of change of the flux through the circuit. You know, any circuit, any closed circuit, defines a sort of a loop, okay, and there is an area that is enclosed by that loop, okay. So think of any loop, any circuit, it forms a loop, closed loop. There is an area. Now, this area, there is the flux here. There is if this loop is in a magnetic field, there is a flux penetrating this area, okay. Now, if this flux is varying for whatever reason is, okay, then the flux where through this area is varying for whatever reason is, then in this case there is an induced electromotive force in the loop, in the circuit. Okay? So you must have a closed circuit. This closed circuit must enclose some area. There must be a magnetic flux through that area, and this magnetic flux must be varying. Now, when this varies, there is an induced electromotive force. The magnitude of this electromotive force is related not to how large is the flux, but how fast is it changing with time. So it's related to the rate of change of the flux, not the magnitude of the flux. Okay, so it's the rate of change of the flux that induces how large is this. The faster the flux changes, or the more is this rate of change, the larger is this electromotive force. When the flux rate of change is 0, okay, then in this case the electromotive force, induced electromotive force, is 0. And this is why we had, for example, in the first demos, you remember we said when you stop your hand, while your hand was approaching the loop, when you stop your hand, now there is still magnetic flux, but the magnetic flux is not changing. In this case, this quantity is 0, so the current goes to 0. Okay, so we didn't have current in that case. Now, the magnetic flux is nothing but this quantity that I have just defined. Now, if rather than a single circuit, you have a circuit that consists of n identical loops, then in this case, the electromotive force, you will have an induced electromotive force in each single loop, and so the total electromotive force induced in the coil will be n minus n multiplied by d phi b by dt.